Okay, so let's get started. So it's my very great pleasure to introduce David Parks. David Parks is Gordon McKay Professor of Computer Science at Harvard University, where he started the Economics and Computer Science Research Group, which is very successful. He got his PhD in Computer and Information Science from the University of Pennsylvania in 2001. He got his Master's in Engineering and Computer Science from Oxford University in 1995. He has won many awards, including a Sloan Fellowship, a Career Award, a Turan Scholarship, many others, also teaching awards, including the Roslyn Abramson Award for Teaching, and he was also named one of Harvard's Class of 2010 favorite professors, which is very proud of. And what else? And so finally, it's very nice to be able to organize something for David, because David is always very active in our community organizing things. He's often program chair, general chair for some of our best conferences, and so it's nice to do something in return. So please, David.
Thank you very much, Vincent. Of course, I should say the same about you. You're extremely active. So very happy to be here. Thank you for inviting me. And I want to give you a bit of a background on mechanism design theory, and then talk a little bit about some of the work that has been happening in the past, let's say, 10 years, and then give my personal view of where I think the field is moving now. So without anything further, let's get started. Mechanism design theory was founded essentially in the early to mid-60s by people like Hurwitz, who started trying to formalize what economic systems are able to achieve. So there's Hurwitz with this idea of incentive compatibility, Maskin with this idea of Nash implementation, and Meyerson with this idea of doing Bayesian mechanism design. The reason I mention these three particular people is they received the Nobel laureate in '07 for their contributions in this field. And the main question that the economic subdiscipline of mechanism design theory asks is this. It's, what can we do in principle despite agent private information and self-interest? So this was a question that was asked at the time of great debate about command and control economic systems versus free market economic systems. And there was a mathematical theory that was developed to try to explain the boundaries between what's possible and what's impossible. Very nice example of this is the so-called median mechanism. Suppose I'm trying to locate a fire station on a single line, on a one-dimensional line, and this is a fire station down here. And suppose that the agents have what are called single-peaked preferences. So each agent has a most preferred location, and then has preferences that fall away from that most preferred location. And the median mechanism says that you would collect the reports of peaks from agents, locate the fire station at the median report, median not mean, and then we can think about the properties of this mechanism. And one thing you notice is that if this agent on the right starts to misreport her preference, then nothing changes, nothing changes, nothing changes, and then at some point she pulls the fire station away from her most preferred location. So she's made the outcome worse from the perspective of her own preferences. Notice that the mean rule would not have this property. With the mean rule, she could vastly overstate her preferences that way, and she could improve the location. And in fact, Moulin proved that there's a sense in which the median mechanism completely characterizes the interesting things you can do in this particular problem. I will say this is strategy proof, and one way to think about why this is a strategy proof mechanism is that this is the choice set that this agent faces. This is kind of the range of things that she could effect, if you think about it. And actually, by being truthful, she's already picking the one that's best for her. Another very classic example, the single item auction. If I'm auctioning off some wine, these are the four agents with their values for wine. And what Vickery proposed was to run a second price auction rather than a first price auction. So normally when we think about an auction, you might think about bidding and then selling the item to the highest bidder at the bid price. And this leads to counter speculation where you need to think about the bids of other people. So Vickery suggested that what you would do is sell to agent 10, but charge him 8, which is the second highest bid. And this makes this auction strategy proof. Now Mr. 10 doesn't have to think about the bid of Mr. 8 here, because by saying 10, he says that he doesn't want to pay any more than 10, and he knows the amount he pays is the highest that is bid by the other agents. And actually, you can also think about this as a monotonicity property. This allocation rule is monotonic, meaning that anything he said above 8, he would win. Okay, so remember that. And you charge the critical value here. Third example, I'll give you. The US government for a while now has been trying to use auctions to allocate landing rights at airports. And this is a combinatorial auction problem because the airlines have preferences over packages of landing rights. If you're US Airways flying from Boston into LaGuardia Airport, up here, you want to express a value for getting 9 a.m. and 10 a.m. and 11 and 12 because you want to run a regular service. And in fact, the basic ideas of the Vickery auction I described will generalize to combinatorial problems like this, when essentially you're solving a weighted set packing problem. Okay, so this basic idea from economic theory was this idea of a direct revelation mechanism. What that means, this was Hurwicz's idea, is that we're going to formulate this problem of trying to figure out what we can do in principle, despite self-interest and private information, as a message passing game, where each agent will simply send a message to a mechanism where the message, here V sub I, is a statement about its private information, its preferences, and then the mechanism picks an outcome and picks the payments that agents make. This is the basic idea. Once you've formulated the problem this way, you can formally define this notion of strategy proofness. So we think about the outcome here as being the combination of the, let's say, allocation of goods that are made as a function of the input and the payments that each agent makes as a function of the inputs. Then I can say that the mechanism is strategy proof if the outcome if agent I prefers the outcome when it is truthful, whatever the other agents report, that's what this V minus I notation is, over the outcome it would have achieved for any other misreport. That's how to read that. So you can formalize this notion of strategy proofness. Okay, so we've seen quite a lot of applications, broadly speaking, of mechanism design over the past, let's say, decades. You can read some of them here. Not all of these, I have to say, are definitively strategy proof, but certainly some of these are. And it's fair to say that economic theory and computer science, more recently in operations research, has guided the development of quite a lot of these systems. Now, Halvarian, who's an economist, actually made the following point in '95. He said that hyperrationality, this notion that agents will play in equilibrium, is arguably the appropriate model for software agents, maybe more appropriate. You'll find its most exciting and practical application when computerized agents are participating in mechanisms than when humans are. And in fact, Rosenstein and Zlotkin had anticipated this point in a beautiful paper they wrote in the early 90s and then became a book in '94, where they talked about this idea of rules of encounter. And they said that as distributed systems of computers become more important, we need to think about ways to design so that they interact effectively. And adjusting the rules of the game by which the programs must interact can influence the private strategies that designers set up. And they had this nice example of these three phone companies bidding for the right to carry your call. And maybe one carrier says, maybe I could manipulate and try to bid more than my true cost for carrying the call. And they basically made the following point. They said that if we don't design the rules of the game well, then these firms will pay programmers to develop sophisticated models, put their energy into trying to discover information about their opponents, and drain resources that could be used elsewhere. And in fact, this has been seen. So if we now go to internet advertising, and if we look to around 2001, 2002, when internet advertising on search engines was just beginning to happen, Overture, as it was then, was using a first price auction to decide how to rank adverts on a search page. And in fact, Edelman and Ostrowski have documented this kind of sawtooth pattern. This is the price for the top slot on an advertising results page. And it shows this competition between two bidders that are bidding up the price to be number one. And then at some point, the price gets too high, and one of the bidders drops down, says, OK, I'm not competing to be in the top slot. I'm going to accept that I'm in the second slot. And then it all happens again. And this was a very reliable pattern. This is data from August of 2002 showing this was happening. And actually, these bidders were employing software agents. So what are you going to do about this? Well, what you're going to do is you're going to try to do some mechanism design. And the solution, which was adopted by Google first and is now adopted by all of the search engines, is to use a generalized second price auction, which is a generalization of Vickrey's auction. And the way this works is that if there are three bidders with these values per click, the search engine will rank the adverts by expected revenue. So the search engine will use complicated machine learning to predict the click-through on an advert. We'll rank the bids by bid per click times click-through rate, so rank by expected revenue. And then we'll charge you not the amount you bid when you get a click, but we'll charge you the smallest amount you could have bid, which is this amount, such that you would have kept the same position in the results. This is an analog of Vickrey's auction. And the reason they did this, arguably, there's some debate about this, but arguably one of the main reasons was that the churn of all of this manipulation on the servers was causing huge inefficiencies. Interesting for the experts in the room, because GCP is actually not quite the right generalization of the Vickrey auction, but interesting that it seems to be stable enough. So it says to those of you that think about the pragmatics of engineering incentive mechanisms, maybe we don't need exact strategy proofness. OK, now, two other reasons why strategy proofness is liked and enjoyed. One point has been made by Attila here and his colleagues about equity when they were looking at the Boston school choice mechanism, which is the mechanism by which Boston students are matched into high schools. The Boston school choice mechanism switched from a non-strategy proof mechanism into a strategy proof mechanism. And in the minutes of the meetings where people were debating this, an equity point was raised, which is essentially that it was the more sophisticated parents that were gaming the mechanism, and the less sophisticated parents were not gaming the mechanism. The other point is just a robustness point, which is if we can get strategy-proof mechanisms, then we don't need to assume very much about the knowledge of agents about other agents. So the mechanism design agenda, then, you can think about it colloquially as being inverse game theory. You're assuming agents play at an equilibrium, and you're going to design the rules of the game so that the equilibrium has nice properties. That's the agenda. And one of the things that I think we've come to realize as a field in computer science is that we can think about a mechanism as an algorithm. It's a mathematical object within mathematical economics, but when we work on it as computer scientists, we think about it as an algorithm. And there has developed this very interesting agenda between economics and computer science about computational mechanism design. Okay. And one of the interesting questions there is I mentioned the direct revelation paradigm. The direct revelation paradigm is wonderful for proving things mathematically, but it's not very useful oftentimes in practical deployed mechanisms because it ignores the costs that agents face in reporting their preferences, right? So a lot of attention has been given to bidding languages, to methods of preference elicitation, to indirect mechanisms. And then the other big avenue of research that's happened over the past decade has both been to take the computational problems that need to be solved within these outcome rules and scale them so we can solve them optimally, and also study approximation agendas where we want to insist on polynomial time worst case, and we want to try to find the properties of the mechanism. Kamesh and his group have been working on those kinds of questions recently, for example. So this has been a very interesting agenda where you think about bringing together incentive constraints and computational constraints. Now, one of the things that we've realized along the way, and this gets to one of the first technical things I wanted to mention, is that actually it's difficult to design mechanisms that are strategy proof. And that used to be a sad face, but I think maybe it should be a happy face because we're researchers. So it's a happy face. So it's actually quite hard to reason about strategy proofness. And if you think about it, we're interested as computer scientists on developing strategy proof mechanisms for problems that are computationally difficult. The typical mathematical approach for designing strategy proof mechanisms involves a lot of analysis using mathematics, kind of deriving optimal things. But we don't really have the right tools to derive optimal algorithms for these problems. So we don't really have the right tools to prove that we have the optimal algorithm, except in some senses. Then you can begin to see why it's hard to find provably optimal solutions here. So of course, Vince and Ming-Yu and others have this very active agenda on automated mechanism design, which is an important part of this problem. And I'm going to talk about a few different things here. So let me, first of all, start by pointing out that the economically optimal mechanism might be somewhere in this space, and let's assume that it's intractable. We might take an approach where we insist on polynomial time. We want to find the mechanism with the best approximation ratio. We might say that we're going to do something called constrained automated mechanism design. So we're going to search through a parameterized family of algorithmic rules, knowing that whatever we pick will be truthful. And what I wanted to mention to you is something that we've done, which is to essentially take an algorithm that you would like to use if self-interest was not part of the problem, and then find a way to kind of perturb it in some way so the algorithm now has nice incentive properties. So you're always working with an algorithm. Sometimes so some of the AMD techniques, for example, end up with a kind of description of the algorithm. And here we're always working with an algorithm. And the particular application I wanted to briefly mention is to dynamic problems. The reason I mention dynamic problems is because one of the things that changes on the internet is that suddenly mechanism design problems that used to be static events with a static population of agents making a single decision, a lot of the times when we're designing internet systems, they're more like platforms. And therefore, there are dynamic decisions that need to be made on an ongoing basis. And there are two types of dynamics you might think about. One is what I call external dynamics, which is the dynamics of agents arriving and departing, maybe bidding for things and then leaving, other agents arriving, maybe you're managing your resource pool over time. And the other type of dynamics that I think is interesting to think about is internal to the agent, which is you're coordinating a fixed population of agents, giving them resources or whatever it is, and their local preferences are changing as they do local things to themselves. So as they learn or adopt new goals, their local problem is changing. Particular example I'll just briefly give you is to a dynamic knapsack problem. So suppose I'm selling M units of an identical item. Say it's some tickets for the theater. And suppose I have a probabilistic model of the arrival process of bidders into my mechanism. And suppose that I model the preference of an agent, that is its type, as a quantity, Q. You want, say, 3 tickets, all or nothing. You only want 3. You have a value V for all 3 tickets, and you have an arrival time and a departure time. So at some point you arrive, and then you're in New York City for the day, just arrived, you go to the ticket booth. You need to have a decision by 2 p.m. because if you can't get tickets, then you're not interested anymore. And there's a seller that's selling a finite supply of tickets, has a probabilistic model of demand that's arriving into the system. So if this was a problem without incentives, this is an MDP with a very special property which you can think about as an exogenous uncertainty property. It's a Markov decision process, but oftentimes in Markov decision processes, the uncertain things that are realized depend on the actions that you take. You're a robot, you're moving around the world, and the uncertain events that occur depend on what room you're in the world. This is a setting where the uncertainty is about the arrival of new demand, and you can model that as being independent of the allocation decisions that you make. So because of that, this fits into a framework that Van Hentenryck and his colleagues at Brown have developed, where you can use a nice relaxation of the online stochastic optimization problem and basically sample multiple trajectories forward. So sample the arrival of demand that might occur, solve a combinatorial optimization problem on each one of those samples, and then try to decide what to do now. This is an online algorithm. It's heuristic. You can sometimes establish bounds, but it's heuristic, but it's fast. You don't have to build out an exponential look-ahead tree here. So this is the kind of algorithm that I think would be nice to use for this problem. And the way you might use it is have your generative model of the world, have your OSCO algorithm up here. It's saying whether or not you should sell to Vince. And if the algorithm has a very useful special property, that of it being monotonic, which is analogous to the property I mentioned at the start, monotonicity for this dynamic problem is going to insist that if you're allocated for some realization of what the other agents do, then you would still be allocated for that same realization if you had arrived earlier, departed later, bid more, or asked for less. Okay, so think about that as being the requirement. If our online policy is monotonic in that sense, then what we can do is we can charge people something analogous to the critical value I mentioned, and it will be strategy proof. And the question is, will this algorithm naturally be monotonic? The answer is no, actually. And here's the idea for what we do. So this is now a non-monotonic function. And what we do is we do a little bit of computational checking. We do online sensitivity analysis. So if the algorithm suggests to allocate, we check that the algorithm would still allocate to you for all higher types. If it would have still allocated to you for all higher types, then we keep the decision. If not, we cancel that decision, and we throw away those tickets. Throw them away. We don't use them. We do this to make the mechanism strategy proof. Okay. So what we do is we put this check, put this sensitivity analysis, computational sensitivity analysis in the middle, and we automatically correct the decision of the online stochastic algorithm. And then we compute critical value with respect to this whole thing. And we actually have been able to get this all to scale. And when we run experiments in simulation, this is the kind of thing you find. If you worry about efficiency, if you worry about maximizing expected social value, then the algorithm without this extra ironing sensitivity check gets about 95% of the offline value for a particular distribution. When we iron, we get down to around 89%. And when we use the best optimized fixed price schedule, we get around 81%. So all I can say is that I took an algorithm, I modified it, I get around 90% efficiency. There is no optimal mechanism understood for this problem because the combinatorics of the problem mean that it's hard to analyze. So this is an example of a heuristic mechanism. Okay. So back to the main thread. We like strategy proofness. It can be hard to work with, like I just mentioned. And it can also have a bad impact on other properties. Let me give you an example of that. I mentioned course allocation on an earlier slide as an application. So at Harvard Business School, they actually use a mechanism to allocate students to classes. You don't just get to register in a class. You have to participate in a virtual market to bid for the right to register in a class. This is fine at a business school. So this happens, and and there's been some empirical work on this that has pointed out the following thing, which is that the unique strategy proof mechanism is random serial dictatorship. So it would just kind of randomly snake around this room. It would point at Jeff, and it would say, OK, Jeff, based on what's not been taken, what package of courses would you like? It would go to Ming Yu. OK, based on what would you like? It would snake around. That would be random serial dictatorship. What actually they use at Harvard Business School is something similar, but they snake around and they just ask you, what course would you like next? You don't get to pick your whole package. You pick which one you like next, is one way to think about how it works. And this is not strategy proof. However, this empirical analysis has shown something quite interesting. It's shown that, so the black line here is the distribution of rank achieved by agents in the RSD mechanism in simulation. So the rank, for example, you're allocating 10 courses. If you get your top 10 courses, your average rank would be 5.5. You get 1, 2, all the way down to 10. That would give you 5.5. So there are around a third of the agents are doing really, really well. But a lot of the agents are doing really, really poorly. They're getting terrible choices. Whereas if you look at the distribution of rank in the Harvard Business School mechanism, as you might expect, nobody's doing really extremely well, but there's a much better distribution of people that are actually very happy. And then for particular models you have of how your preference falls off as you go down your rank list, then the non-strategy proof mechanism is actually much better than the strategy proof mechanism. OK. So if we don't want strategy proofness because it has all these costs, what else might we do? Well, one thing that we might do is we might use regret. Regret is a very simple idea. Regret says that you regret your decision if, after the fact, after you've seen what everybody else has done, you have left this much utility on the table. And then we might design the min-max regret mechanism. So find a mechanism that minimizes the maximum regret over every agent for every instance. And the idea would be that if the regret is small, then agents will choose to be truthful because it's too costly for them to think about their manipulation, and they don't want to go to the trouble. And to give you an example now for my second technical chunk here of the kind of thing that you can then do when you think about the world this way, we've done some work on combinatorial exchanges. Combinatorial exchange is like a combinatorial auction that I alluded to for the airport landing rights allocation problem. But it's an exchange because there are multiple buyers and multiple sellers with complicated preferences. Maybe they want to do swaps, contingent sales. And you can think about using a combinatorial exchange amongst a community that's trying to reallocate the things that they own. Here are some examples of what you might like to say. Now, the reason the combinatorial exchange problem is interesting is because the Vickrey generalization fails miserably. And the reason it fails miserably is it runs at a huge deficit. So if you want to use Vickrey's idea for combinatorial exchanges, you have to actually basically pump a lot of money into your market. Because what you have to do is this is what I call the VCG discount. This is how much money, how much more value the system achieved with you than it would have achieved without you. And basically in VCG mechanisms, you have to discount the amount that people bid by this amount. So in my second price auction from earlier, the discount would have been the difference between 10 and 8. So you get a discount of 2 and you pay 8. Now if you stack up the VCG discounts in this problem and add up the space you have to redistribute, which is all this space, it will be more than the money that's left on the table when you clear the exchange. And also, the other thing you should know is that your payoff, your utility as an agent in such an exchange, is the discount. It's the amount by which I discount, because you're being truthful when you bid. OK. So this is what VCG would do. It would allocate all this discount back. This would be the payoff distribution for 1, 2, 3, 4, 5, 6, 7, 8 agents in a particular instance. And I've just ordered them from high payoff down to low payoff. But we can't do that because we don't have enough money. So what are we going to do? So back in 2001, what I had proposed was the following. I had said that the thing you should do, one other thing. If I only give you part of that discount, then your payoff is this much and your regret is this much. Okay. So in 2001, what I had proposed with some IBM colleagues was that you would do the following. You would kind of trickle the money down from the top. You would use what I call the threshold mechanism. And this minimizes maximum regret. You can kind of see it graphically. Minimizing maximum regret. Remember, regret is this distance. So now this is the way to minimize maximum regret over the agents. Another thing you might do is the small rule, which is this. Kind of trickle the money from the right. Try to make as many people exactly happy as possible. That's the small rule. So for 8 years or so, I thought this was the right thing to do, the threshold rule. And Ben Lubin and I recently did some approximate Bayes-Nash equilibrium analysis of this system. Ask me the details later if you want to know how we computed approximate Bayes-Nash equilibrium here. It's quite hard to do, and it's approximate. But I think the results are qualitatively correct. And for different distributions and for different rules, we computed the amount by which agents strategize, the amount by which they shave their values down in each of the 4 mechanisms, ignore the 2-triangle mechanism, and the effect that had on the economic efficiency. Okay, so VCG, they don't strategize. It's 100% efficient, but we can't use it. Threshold, they strategize a lot, they deviate a lot, and the efficiency suffers. Small, they basically are truthful in this equilibrium, and the efficiency is great. So I was shocked, wanting to understand what was going on. So this says that min-max regret is not the right thing to do if you believe these results, which I think I do. So one thing you might do is look at the distribution of discounts, the distribution of payoffs in the system under the VCG, which is here. So lots of agents. So there are say, around 10% of the agents make no money. And then you can see how the distribution is. Notice small, the blue line follows that really nicely. I notice the threshold gets that really badly wrong. Threshold has a lot of agents, 50% or so, getting no payoff, because those are the ones that were over on the right-hand side of my earlier plot. So one thing that we found this is a UAI paper from 2009, one thing we found is that if you take the KL divergence, that actually, between the VCG reference mechanism with this distribution and these other mechanisms, that is indicative of closeness between the Bayes-Nash equilibrium and of how far the Bayes-Nash equilibrium deviates from being truthful. But then the other thing that we did was we plotted the regret quantiles. So we looked at the distribution of regret to agents in these systems. Here's what happens if you don't give any money back. Every agent, so the agents are, leaving around $0.50 in these experiments on the table. Here's what threshold does. Minimizes the max deviation. So this is the lowest on this axis. And here's what small does. This is over many, many experiments. Small pushes the percentile at which people start to have some regret really far along this axis. for only suffering what looks like a pretty small fall off in the max regret. So we're getting all this gain here for just maybe a pretty small effect here. And so this tells me that one thing we can do as a proxy for trying to design approximately incentive compatible mechanisms is to try to push the fraction of agents with small enough regret to be as high as possible and make a trade-off with the max regret. And it looks like an interesting trade-off. OK, that's what this is. So I think this is another example of a direction in doing pragmatic mechanism design. By the way, there are some other concepts in the literature for approximate strategy proofness that I'll skip over in the interest of time. OK, so back to Rosenstein and Zlotkin. The other thing they did in their work from early 90s, mid 90s, was to talk about task allocation problems, action coordination. So they had this nice example, I'm sure some of you have seen, of two agents that work at the post office and have tasks that they need to do. Agent 1 has to deliver some mail here and here, agent 2 here. They have to deliver the mail and go back to the post office. And it costs $1 for every edge you have to traverse. So one mechanism you might think about is somehow asking the agents to report the work they have to do, and then giving an efficient allocation of that work. So if the agents are truthful here, it's pretty clear that the efficient thing to do is to give all of the tasks to one of the agents and have that agent do the whole loop, and the other agent doesn't do any work. Now, actually, what agent 1 can do is agent 1 can hide this task, pretend that he only has to do this task down here, and now you have to ask agent 2 to do these two tasks. You can't ask agent 1 to do this task, because it would be more work than it's originally doing. And so now agent 1 only has to incur the cost of this task up here. So the agent has hidden some tasks from the system and has been given less work to do. Okay. The reason I'm telling you about this is I think that one very exciting direction right now is moving away from mechanism design and towards designing systems for crowdsourcing or for tasking. And Amazon Mechanical Turk is one leading example of this, where a lot of information tasks are being posted. They're being worked on for small amounts of money. But there are also these interesting competition platforms, like Innocentive and Topcoder, that are having people compete to try to solve problems and do work. And this by itself is not a new idea. But actually, the idea of using competitions to get people to do work goes back to the 17th century in England, where the Royal Observatory launched the longitude problem, which was a challenge to get people to develop technology to let sailors know where they are in longitude, wherever they are at sea. The basic idea was that if you have an accurate clock, and if you can tell where the sun is in the sky locally, and you have your reference clock, then you can compute where you are. So what you need is you need a really accurate clock. And this guy actually worked on it from 1730, finally won the prize in 1773. So he was working on it for his whole life and developed this amazing timepiece. So the idea of competition platforms is not in itself new, but this very rapid integration of partial solutions is new. Very nice example is the Netflix competition. So Netflix announced this challenge. We'll pay $1 million, improve the quality of our predictions for which movies you like by 10%. And around 3 years later, the Bell Core pragmatic chaos team won. And the interesting part of this story is that the competing team, the ensemble, all of these teams were essentially at the end working by bringing together multiple learned classifiers. And those are like the individual classifiers, and there's this meta problem of how you blend them together. So this other team, the ensemble, first of all tried to, it started with Gravity and Dinosaur Planet that tried to come together into a team. those became the grand prize team here. And they were still around 1%. They got a 9% improvement. They had 1% to get still. So what they did was they announced in January of '09 that they would share 2/3 of the prize for the final 1% improvement. And they would basically pay that amount in proportion to the amount by which your new classifier that you introduce into my ensemble improves my accuracy. So then they made improvements, 0.21%, 0.14, 0.06, 0.08, 0.19, till finally June '09 was the date that the other team said they'd hit the barrier. And that's when Netflix rules you have another month. Then they said, OK, then these three all came together and they finally got another improvement. They got to 10.1%, which was about the same as the winning team, but they missed it by about 1 or 2 minutes. So this is interesting in that they kind of designed an incentive scheme to try to get people to work together in a very simple way here. And in fact, collaborative problem solving, you see a lot of this. The Polymath project is a very famous example. Another nice example is the Galaxy Zoo project. So you can find out more about volewerp hunting if you're interested in this. Do a Google for volewerp hunting, read about that. Which means blue. No.
Foreground means object.
Object, OK. She is Dutch, of course. She's a Dutch high school teacher. OK, final thing I want to mention as a motivation for this new direction is the DARPA Grand Challenge for red balloons. How many people have heard about this? This is a really nice example where DARPA wanted to try to locate 10 balloons quickly and reliably. So they said, we'll pay $40,000 for the first team that will find all 10 balloons. They'll be released at a particular time at 10 locations in the US. It was won very quickly. Those where the balloons are. And the team that won was the MIT team. They had this recursive incentive scheme. Basically, the way it worked is, and here they are celebrating here. If you find a balloon, you get paid $2,000. Remember, there was $40,000, 10 balloons, so $4,000 for each balloon. And it's this recursive divide by 2 thing. You get $2,000. The person that recruited you into the network gets paid $1,000. The person that recruited that person gets paid $500. It kind of recursively trickles back like that. And then whatever money is not given out goes out into charity. OK. So they actually recruited a lot of individuals in a short period of time, and this virtual supply chain to solve a problem. Pretty interesting, I think. This is an interesting computational artifact. Ariel Procaccia, Felix Fischer, Iyad Rawan, and I thinking a little bit about this right now, and it's actually brittle in that it's not false name proof. So actually, if you find a balloon, you should recruit all these extra people in your family and kind of quickly recruit them and then report you found the balloon, and then you suck up all of this money. Okay, so open question, how to make this false name proof and still useful. So what's going on here is we're shifting from mechanism design, which is listing information and then making a decision, to what Haoqi Zhang, students at Harvard, and I think about as environment design. So environment design is about eliciting actions rather than about eliciting information. So you're somehow you're perturbing the incentive environment of workers, trying to get them to do useful things. And just to give you a very simple example of this, we worked on, which is policy teaching, and it's related to inverse reinforcement learning. So suppose that you have a target policy in mind you want an agent to follow, and it's in a Markov decision environment. And suppose you can observe its policy, then and you have a target policy. The idea is going to be to, that's its true reward vector, let's say. This is the IRL constraints. You're kind of observing what it's doing, and you're understanding something about its rewards for different actions. And you're going to guess where its reward is. You're going to then perturb. You're going to guess where its reward is. If its reward is there, then you know that if you perturb its reward vector by this vector delta of incentives, then its new policy will be your target policy. So you do that, but its reward is actually here. And then you get new constraints because you observe new behavior, and you add new constraints, and you go again. OK, and you keep going. So that's just one very simple example. What I think is interesting about all of this, I think there's a new Econ CS challenge here, which is kind of bringing together AI and these tasking, crowdsourcing systems to design new kinds of firms. Maybe we don't need the kinds of firms we have right now. Maybe things can be much more decentralized and coordinated in other ways. And this is a bit of a pun. I apologize if you don't find it funny. Amazon Mechanical Turk is so named because there was a Mechanical Turk from, I think, the 17th century that toured around the world and seemed to be this robot that played chess. It actually had a really tiny guy in here that was actually playing chess. This is called the Mechanical Turk, and it was a fraud. So Amazon Mechanical Turk is basically, again, using people to do smart things. And I think maybe now we can put the AI into the Mechanical Turk, because it wasn't AI there, but maybe now we can make it intelligent. Okay. So people are working on this. Eric Horvitz and Daphne Shahav, she's at CMU, had a nice paper at AAA 10 where they're trying to optimize basically task routing for language translation into Amazon Turk. Trying to decide, should you use a computer to do the translation? Should you use a person to do the translation? Or should you use a person whose quality is not so good, and then a computer, or a computer and then a person? So you imagine different combinations of routing work. And they did an experiment with this, and let me not dwell on the results, but they have some interesting results. More really interesting examples, Rob Miller's group at MIT and his PhD student Greg Little and their group have been working on a platform they call Turkit, which is a scripting language to program into Amazon Mechanical Turk. And one really cool thing they've done recently is a Soylent system, which is basically a button in Microsoft Word. You write a paragraph, you push the button, and then in the background, it takes about 20 minutes, that paragraph goes off onto Turk and is proofread and improved by the crowd through a find, fix, verify programming pattern, and comes back into your document improved, is the idea. Right? So then there are AI people at UW who are working on optimizing workflow using Turkit, and we have a paper from HComp this summer looking at automatic task design. So examples of AI challenges in this space. One interesting thing is that we do need better user models. This is an empirical study from EC10 this summer by some economists at Harvard that looks at, this is a bit of a complicated graph to read. So for example, if you look at this line at 15, this is the, let's see, 15 divided by 5. Okay, so this is the height of this bar 15 is the amount of people that worked in the system and achieved a final earnings of 15 cents. That's the height of this bar here. The height of this bar is the amount of people that worked in the system and earned a total earnings of 23 cents. Okay, do you see how to read this? This is the amount of people that worked in the system and earned 27. This is what I'm saying, approximately right. The interesting thing is that the height of these bars is dominated by multiples of 5. So somehow there was this anchoring effect where people were trying to achieve multiples of 5 cents in the work that they were doing. And you see this in quite a lot of economic systems as behavioral property. So this shows that we need better user models if we're going to optimize these kinds of systems. Another comment I wanted to make is that to be really successful here, you need to collect meta information, reputation feedback, quality, etc. Topcoder has a very elaborate reputation system where they compute and share a lot of statistics on the workers that are doing software engineering tasks. And this is, I think, extremely exciting because as a field within AI and theoretical computer science to some extent, we've been developing reputation algorithms for about a decade. And now I think that we can begin to apply them to these kinds of systems. And it's both about accounting how much work did you do and reputation, the quality of the work. And Sven Soyken and I have a paper at AAA 10 about incentive-compatible accounting, for example. Okay. One of the, I think, most exciting challenge problems then to motivate this whole field for students in the room is, I think, for me, is given by this quote of somebody's experience living in the hutongs in Beijing. This was an American living in Beijing and explaining his experiences of living on these alleys and hearing people riding around selling beer, selling rice, selling vinegar. Life was sustainable, could have cooking oil, soy sauce, vegetables. Winter could buy strings of garlic. On an average day, a recycler passes every half an hour. Powered some possessions, old magazines, burned out computer, went for a nickel, broken lamps, went shoes, Palm Pilots. So it's kind of living in this very small, cramped locations, not really owning very much in your home, but sharing things and buying and selling things in small quantities. And I actually think that we can try to develop new kinds of electronic markets to be more sustainable in the resources that we use in our living in the US. I think it's kind of shocking how many things I have in my house that I'm not using. And we should be able to do some things here using some of these ideas, I think. So it's kind of a peer-to-peer for people rather than for file sharing. Okay, and one part of this, I think, will be this notion of hiding the complexity of markets from users. Sven Soykin and colleagues at Microsoft Research have been doing some work on this where they've got a peer-to-peer system for distributed backup. And essentially, there's this interface that lets you kind of interact with the system, say how much bandwidth you want to contribute, how much disk space you want to contribute, in return for secure, trustworthy distributed backup, where there are prices behind the scenes that are affecting the rate with which, if you move one of these sliders, you get more service. But it's all hidden from the user. The user doesn't know that she's interacting with a market. And I think this is an example of a nice line of research where we'll need to think about things like this if we want to use these lots of microtransactions happening all the time that are hidden from us, because we don't want to worry about all those details. It involves UI design, AI, and market design. Okay, so wrapping up now, I started talking about preference elicitation, which is the traditional model of mechanism design. I talked about this idea of action elicitation, which is like the principal agent model in economic theory, but that tends to be one principal, one agent. So I think it's considerably richer than that. And then just one other thing I wanted to point out, I think about this as being a little bit different, which is information elicitation, collecting knowledge from people, rather than collecting preference information, collecting opinions about things. So this third axis is this information elicitation axis, where the work that participants are doing is providing information or knowledge. And you could think about things like prediction markets, things like Yahoo Answers, things like collecting labels for supervised learning. Ariel Procaccio and Felix Fischer have done some of the leading work on this. They're at Harvard at the moment. My student has done work on the Yahoo Answers, Shali Jain, and my colleague Yiling Chen works on prediction markets. And we're also thinking a little bit at Harvard now about data markets. There's a big project involving people from the Berkman Center, which is a university center involving the law school, where we're thinking about legal and technical and economic implications of letting people basically contribute personal data to a shared marketplace to enable new kinds of social science, medical research, and things like that. This is not happening right now, and it's a very deep, interesting problem, I think. Final comment I wanted to make that I didn't mention in terms of incentive engineering for the internet in the internet age is to do with trustworthiness. Of course, there is this traditional, at this point, econ CS view of security challenges for systems, where you should worry about the incentives of people adopting new security. Ross Anderson and his group has been leading that, I think, over the years. And then I wanted to point out that there are new questions and concerns. So if you move to crowdsourcing, what's the appropriate notion of trustworthiness for crowdsourcing systems? Think about these as distributed computational systems. What would it mean for it to crash? What kinds of attacks might you expect? Things like that. There's a project at the Berkman Center called Verdict Web, where they're sourcing internet outages from all around the world because governments will censor internet sites. And that's the type of system you could imagine being attacked. So to summarize, there are a lot of really exciting design challenges at the moment in academia that we can think about and we can help industry to think about. And I've kind of bucketed things into these three spaces. And for the students in the room, I really encourage you to get into this area. There's a lot of fun things going on. And I have a lot of people to thank that I don't have time to thank individually. But thank you, all of my colleagues and collaborators, and my funding agencies. And if you want to find out more, we have an EconCS webpage at Harvard. So, thanks.
So, David, what we'll do is we'll take questions from the other places first.
Good. OK, so we'll take questions from the other places first. Does anybody at NCSU have a question?
One of the things the market depends upon is ownership and property rights, and there are other sorts of properties that go into things. So when you gave your example of the crowdsourced proofreading, who is the author of that document?
Right, good. And there are privacy implications there as well, obviously, if you start to actually farm out paragraphs into the crowd there. In terms of the author of that document, I don't know what the contractual terms are there. I believe the way Amazon Turk works is that the person that's asking for the work to be done owns the results of the work, and the workers don't own that work. I think that's the contract the workers have with Amazon.
What would be the contract between somebody that author submits that work to as their own?
I see what you mean. Yeah, right. So there are implications perhaps for, for plagiarism within university environments, for example. Yeah, that's a great question. And I think that gets to trustworthiness as well, in the sense that that would be an example of a non-trustworthy crowdsourcing system if what the crowd is doing is plagiarizing in returning the text that's being, in returning the text. And I think that's a great example, yeah, of some of the challenges in this system. Other questions from NCSU? OK, questions from UNC? OK, questions from Duke? Kavesh?
So you mentioned your mechanism your method for making a mechanism monotone. So how is it related to Meyerson's ironing procedure? Is it
okay.
generalization?
So the question is how does the sensitivity work that I described for the online stochastic optimization algorithm relate to Meyerson's ironing work? Those of you that don't know, Meyerson is well known for innovating optimal auction design for selling a single item. And when things are well behaved, everything is monotonic and there's no difficulty. But sometimes the distribution function is such that the allocation rule is non-monotonic. And so Meyerson tells you how to basically smooth out the non-monotonicity. So if you have a function like this, Meyerson would say that you cut the trough so you kind of balance things out and then you make it monotonic. So I think about what Meyerson does as input ironing. Basically what he's doing is he is he's perturbing the input into his optimization algorithm such that he can prove that his optimization algorithm is monotonic. And I think about what we're doing as output ironing. What we're doing is we're doing sensitivity analysis on the decisions of the algorithm itself. And the reason we're doing that is because I don't have the kind of mathematical analytic results here to be able to understand what properties we need of the distribution such that the algorithm will be monotonic. Anything else? Vince?
So you mentioned that strategy-proofness might be a little bit too strong, and so we might want to weaken that a little bit. But so, do you have any sense of how we can have a good general theory of not quite strategy-proofness, but still being effective in practice? So you saw some examples.
Yeah.
You mentioned some examples of that. But maybe repeat my question.
I'll repeat the question. So, question from Vince Condenser is, we need something like approximate strategy proofness. Are there any useful general theories that we could imagine to provide that? Obviously, I mentioned this idea of regret and thinking about maybe trying to maximize the number of people that have very small regret as a way, actually, I claim, to push the Bayes-Nash equilibrium towards being truthful. That's one thing I think is interesting, but it needs much more empirical work. Other concepts that are out there right now, one is this concept of spittle due to Budish, who was at Harvard and is now at University of Chicago in the economics department, which is strategy proof in the large, which basically says that the choice set, remember I mentioned the choice set, that the choice set should become agent independent, independent of your preferences as the market gets big. So it's like it becomes strategy proof as the market gets big, and the market always has a property that you get the best thing in your choice set. That's one concept. Then Patak and Sommes have this thing about counting how many manipulations are available. It's somehow not very quantifiable. Well, it is very quantifiable, but it's not involving utility magnitudes. And then Erdal Klamperer have this thing about kind of, it's nicely strategy proof if there's no local perturbations that bring a lot of return. So it should be flat with maybe some jumps and be flat again. So I'm not answering your question. I'm saying four things that are there, and I think this is wonderfully open and needs to be worked on. These are all very, very recent working papers within economics. So you can see that lots of people are trying to think about this right now. Yes?
When you talked about your dynamic mechanisms, you talked about some internal dynamics and
Yes.
how. So in that, when you account for that, do you need to separate between a scenario where you have perfect information about preferences, but those preferences are changing, versus you have some imperfect understanding of the preferences and your model of those preferences is improving? Do you treat those differently, or are they?
Okay. So the question is about the internal dynamics, and whether you have to think about the following two things separately. One is where the preferences are always known by an agent but are changing. And the second is where the preferences are uncertain and are being refined, let's say. So the second one to me sounds like learning. And the way that we handle learning in our framing is through the Bayesian optimal learning approach. So we basically think about a Markov decision process where the state is the information state, and the prior gives you the transition function into next states. So you can kind of capture within the NDP formalism this idea of Bayesian learning. Now, so formally you can do things that way. The problem is, and there's been work on this in RL by Mike Duff out of UMass as his PhD thesis, is that if you handle information states this way, you get these kind of hyper MDP models that are too large and are unmanageable. So technically, I can actually handle both of your models within my framework, but the second one gets to be computationally intractable. Okay, thank you.